Okay, so we're going to be starting chapter 4. And chapter 4 talks about Extrema. So before we do anything, we need to know what is Extrema. So we have a picture here of a graph. Now, I'm going to say certain things that will make more sense later, but this is a graph of the original. This is the original function, not a derivative, nothing like that. This is a graph of the original function. And when we say Extrema, we can say local or relative. We have a local max and we have a local min. When I say Extrema, what we're talking about are the highs and lows of the original graph. The highs and lows of the original graph. So looking at this graph, you're going to notice that we have some low points. And we have some high points. These low or high points are called extrema. Those are called extrema. The ones that are not this one, sorry, not this one. Okay, the ones that are the high points, those we're going to call local max. Another textbook uses relative, but local or relative max. The low points, those are called our local mins. Now, you may be wondering, why do we need to find these extrema, these highs and lows? Well, we want to maximize revenue. We want to maximize profit. We want to minimize cost. So we want to find where the high points and the low points are. Now, in the process, you may find these in-betweens, these in-betweens, these in-betweens. These are not extrema. Those are not extrema. Those are not extrema. They're not highs and lows. They may show up. They may be part of it. But every time we find extrema, we always like to go to the original graph and verify, is it a max or a min? Because the process we're going to do may show that it's high, that it's low, things like that. Okay? So let me give you another quick example of that. So I'm going to draw a graph, just going to make it up. And just because you have the picture, you're able to answer a bunch of questions, okay? So I want you to look at this, and we're going to look at the graph, and I want you to answer how many extremas are in this graph. How many extremas are in this graph? Take a minute. Don't say anything yet. Start counting in your head. How many extremas, we just learned what the topic was, do you think there are? Just take a guess. Go ahead and guess. 4, 5. It's like we're bidding 6. Anybody 7? 7 going once, going twice, going there, going 5. So I hear something between 4 and 6. Well, the answer is 1, 2, 3, 4, 5, 6, 7. Now, you've never seen this before. And now you're finding out that there are 7 extrema, 7 highs and lows of the original graph. Now, those highs and lows, instead of just saying all extrema, I'm going to give you categories. And those categories are going to be stationary, singular, and endpoints. And we're going to get into big detail about these today. But these are the types of extrema that will show up. Now, stationary is your typical high and low. So this would be a stationary 1. This would be a stationary 2. This would be a stationary 3. This would be a stationary 4. And this would be a stationary 5. So we have 5 stationary. When I use the word stationary, it literally means top of a mountain or bottom of a valley. That would be the one you normally think of when I say extrema. But there are other kinds too. The other kinds are singular. For right now, singular means a sharp corner. So we have a sharp corner. It's a little tough to see, but it kind of looks like that. We have a sharp corner right here. So we have one singular point. That is another way an extrema can look like. And we have an endpoint right here. That is another possible extrema. So extrema are the highs and lows, but we're going to make it a little bit easier by saying there's three types. Stationary, top of a mountain, bottom of a valley. Singular, those sharp corners. And endpoints, where it begins or where it ends, one or the other or both. Okay? But the good news about everything, before teaching you anything, if you have the graph in front of you, you know how many extrema there are. You know how many stationary, you know how many singular endpoints just by looking at it. So my method, the textbook's a little different, is to get the graph. If you can get the graph, the answers are staring at you. But there are other ways. But we're just learning what extrema are. So let's kind of step back a little bit and let me just show you some examples. So if this was the graph, how many extrema do you see? 2. 1, 2. So we have 2 extrema, and both of them are stationary. Okay, we would call this a local max, and we would call that a local min. Okay, and again, just kind of learning what it is. The arrow means it goes up forever, and the down arrow means it goes down forever. So those are not extrema because they don't end, they just keep going. Okay, let's look at some more. Now, the book likes to use something called a sign chart. I will show you the sign chart, but I'm not a big fan of it. And it's not bad. I just like having the graph. If you have the graph, you don't need a sign chart, but both take work. It's not like my way is better and their way is not. It's just two different ways. Mine's going to take a little bit of work. Theirs is going to take a little bit of work. But if you're looking at a particular point, let's call C, how do you know if it's a max or a min? Well, if you look at the left of it and it's decreasing, then the right of it is increasing. Therefore, this must be a local min. Now, notice what's increasing or decreasing? The derivative. If you plug into the derivative and you get a negative, that means the graph is decreasing. If you plug into the derivative and your graph and you get a positive result, that means your graph is increasing. So if it's decreasing, then increasing, you have a local min. So this is how derivatives are going to come into play. Okay. Now, what if you're looking at point C, but you plug into the derivative on the left side and you get positives? That means the graph is increasing. If you plug into the derivative and you get negatives, that means that's where the graph is decreasing. Now we have a what? A local max. Why? It's going up and then going down. That creates a max. That's the definition of a max. To the left, it's lower. To the right is lower. It's a max. Okay? Now, what if we're looking at point C and it's increasing by plugging into the derivative and then increasing again? Is that a max or a min? That's a neither. Sometimes we may get a point that doesn't work. It's not extrema. And you would find that point by one looking at it. This goes up and up. That's not an extrema. It doesn't go up and down or down and up. Or you look at the sign chart and it just keeps increasing the whole time. It's neither a max nor a min. Okay? And it could be going the other way as well. If it's just decreasing the whole time, it's not a max or a min. This would be neither. So again, I like having the visual. I like having the visual. But the sign chart does work as well. Okay? So again, that would be a local min, just to give you some pictures. That would be a local max. Again, just giving you some pictures of what it looks like. That would be neither, because it goes down and goes down. That would be neither, because it goes up and goes up. Okay. Then we start looking at some interesting ones. Again, this one still goes down, still goes up, plug it into the derivative, and it forms a sharp corner. That would be a local min, but we would call that a singular point. We'll talk about what all that means, but that's what a singular point looks like. That would be a local min, and that would be a local max. Again, same thing with the sign chart. Goes up, goes down. And then again, this would be a neither. This keeps going up. Oops. And again, this would be a neither. Again, you can compare it to the sign chart when you plug into the derivative. Okay, so I'm going to go back. Sorry for the scrolling. And we're going to start from scratch. Now, the first example I'm going to give you has the picture. Normally, you don't have the picture. But this one does. But here's the understanding. Here's the original function. And here's the graph of the original. Now, just by looking at it, how many extrema do you have? 1, 2. We have 2 extrema, and they are both what? Stationary. Now, if we had an endpoint, there'd be a dot on one either of the ends or both. And if we had a singular, it'd be a sharp corner. But the good news is, the way I like, is if you have the graph, you already know there's 2 answers. And you could, if you have a nice graph, you could already find out what the answers are. But I'm going to give you a little formal notes of how to find them. So number 1, remember the question is find the extrema. And we're finding the extrema of the original. It's all about the original. It's the extrema of the original. Like, why does it keep saying that? You'll see why in a minute. To find the extrema of the original, we're going to do 3 things. We're going to look for the stationary, which is the top of the mountain, bottom of the valley. We're going to look for any singular points, that's sharp corners. And we're going to look for any endpoints, which would be where it begins or where it ends. That's the process for extrema. Now, how do you find stationary? How do you find singular? How do you find endpoints? The first one, stationary. How do you find stationary? You take the derivative, which would be 3x squared minus 3, and you would set it equal to 0 and solve. Now I'm going to pause there for a minute, and I want you to practice your algebra, because number 1, you need to know how to take a derivative. The derivative of x cubed minus 3x is 3x squared minus 3. Number 2, you have to set it equal to 0 and solve, which means you need, as always, algebra. So solve that. Again, I'm not going to teach algebra from scratch, but I will go over it with you. You're going to add 3, 3x squared equals 3, divide by 3, x squared equals 1. Be careful when you're starting with x squared. Yes, you're going to square root both sides, but what's going to be my answer? Positive and negative 1. There are 2 answers, not 1 answer, 2 answers. So if you only come up with 1, you're not going to find another point. So here we have 2 points. We have positive and negative 1. Okay? 2. Singular. How do you see and check if you have any singular points? And the answer is, you look at the derivative. There's the derivative. Is there any number that would make this undefined? Now remember, what's undefined? Undefined is like dividing by 0. So if there's a number that you would plug in that would make this undefined, that would be a singular point. Number 1, is there any dividing going on at all? Is there any chance that this could be dividing by 0? Are there any singular? None. But how do you check? You look at the derivative. You look at the derivative and see what number would make it undefined. And we're going to get into that a little bit later. But it's whatever number makes it undefined. Now, endpoint. Endpoint would be given to us when they give us a domain. A domain's like start here and here. Did they give us any domain, where to start, where to end, anything like that? Nope. So there are no endpoints. No endpoints. Now, the deal with this process of stationary, take the derivative, set equal to 0 and solve. Singular, look at the derivative, see where it's undefined. Endpoints, look at the domain, is to give us potential candidates for Extrema, but it doesn't say for sure. You don't know for sure until you check it. So how do we check it? Well, we're going to make a table. We're going to make a table. And in that table, we're going to look up each point and we're going to verify if it's an Extrema or not. So in this process, what points did we come up with? -1 and +1. Good so far? Now, remember, this is where people get confused because we're doing derivatives, we're doing original. We're trying to find the Extrema of the original. So what are we going to plug it back into? The original. Why? It's all about the original. So let's use our calculator, as we've learned. Let's go to y equals. Please make sure your plots are off. Minus 3x. Okay, so remember, we're doing the Extrema of the original. We're doing the Extrema, which goes back to the original. Okay, so I put my original in y1. I go to the table feature. Remember, when you hit second window, it should be ask auto, not auto. When you go to second window, just double check that it's ask auto, not auto. And then go to your table and let's plug in -1 and 1. When you plug in -1, you get 2. -1, you get 2. So I'm going to go look at the point -1, 2. And when you plug in 1, you get -2. So my other point is 1, -2. Now, those are my possible Extrema. I'm going to go check if they are. Now, good news for you, the graph is already there. Normally it's not. Okay, but since it is, let's take advantage. -1, 2. Is that an Extrema? Yes or no? Yes. And what is it? Local X. And remember, this came from stationary. Let's look at the other point. 1, -2. Again, that came from stationary. What do you have? Local min. So in this process, stationary singular endpoints, we found a local max and we found a local min. We found a local max and we found a local min. Are we okay? Now, normally you don't have the graph. We would make the graph ourselves, which we will in the next example. But since we have it, we'll use it just to kind of start basic. Are you with me? Now, what I just showed you, except for doing the graph, that's what I would do to find the Extrema. Your textbook is suggesting another way. The other way is called a sign chart. Again, it's a good way, just not my preference. So let me explain to you how to do a sign chart. The same step 1 stationary, you would find these critical points. They call these critical points that -1 and 1. You still do the same first step and you find the critical points. Are we okay? How do you do it? Take the derivative, set equal to 0, you found your critical points. Then you don't do a graph, you don't do anything else. You just say, hey, what's happening before -1? What's happening between -1 and 1? And what's happening after -1 by plugging into the derivative. So let's go to the calculator. Let's go to y equals. Let's get rid of, let's plug in the derivative. The derivative x squared minus 3. So again, if you're using the sign chart, you're plugging into the derivative, not the original. And then we're going to test in the table, go to the table, go to the table. Let's test some numbers that are less than -1. So call out any numbers that are less than -1. -2, what else? -3, what else? -4, what else? -1.1. And you notice that all these solutions are what? Positive. That means everything less than -1 is positive. So anything less than -1, the graph is going up. How do I know up? Up means goes, positive goes up. Okay. Now pick some numbers between -1 and 1. 0, 0.5, 0.2. What about -0.5? Okay. All these results are negative, which means the graph is going downward. So if the graph goes up and if the graph goes down, what do we know is happening at -1? We have a local max. How do I know that? Even without the graph, it goes up, it goes down. Therefore, that must be a max. Are we okay? Now, let's talk about after 1. So give me some numbers after 1. 2, 3, 4. All these results are what? Positive when we plug into the derivative. So again, it goes down, then it goes up, which means what do we have at +1? A minimum, a local minimum. Now, could you do both? Yes, but I think it's going to get confusing. Okay, so know that a sign chart is good. It works, but I like this one. The work is you're going to have to get the graph to use this. The sign chart, you don't have to get the graph, but you got to plug all those numbers into the derivative. So both of them are work. There's not like easy way, hard way. They're both going to be work. I like the showing the work, have the graph, because you're always focused on the original. Here, people get a little lost. Am I plugging into the original? Am I plugging into the derivative? Why am I plugging into the derivative? Because the derivative is going to tell me up or down. Okay. You have to get that clear. Okay. So maybe you're going to do the sign chart. Maybe you're going to do it the way I prefer. Your choice. But let's practice it on the next one. Okay. So the next one, you're given a function, but you're not given the graph. So the way the question is going to be asked is I want you to find the extrema of f of x equals 8x minus x squared. So all I want you to do, given that, all I want you to do is do stationary singular endpoints and then stop there. Stationary singular endpoints. I did not give you a domain, but just do stationary singular endpoints. So how do you find stationary? Number one, you have to know how to take the derivative. The derivative of 8x is 8. The derivative of minus x squared would be minus 2x. We set it equal to 0 and we solve. We subtract 8, negative 2x equals -8, divide by -2, divide by -2. We get x equals 4. What does that mean? We have a potential extrema at 4. I don't know yet, need to check it. Don't even know what the y is, I just know the x, but we have that. Singular, I know it's a little weird until we do more examples, but for singular, we look at the derivative. Is there any number that when I plug it in would make it undefined? And the answer is none. Why is it none? Because there's no dividing. There's nothing in the denominator. There's no variable in the denominator. There's no chance of that. And we'll deal a little bit more with that a little bit later. It's rare. It happens. It looks like a sharp corner. Okay, but we don't expect any sharp corners here. And then endpoints, do we have any endpoints? The answer is none, because there was no domain. Soon there'll be a domain. Soon they'll be singular. But for right now, we don't have it. It doesn't tell us start here, end here. Okay? So we can make a table, but the only thing we're going to check is what? 4. And are we going to plug it into the original or the derivative? The original. Why the original? Because it's all about the original. We're trying to find the extrema of the original. So we go to our calculator. We go to y equals. We clear the old one. We put in the original 8x minus subtraction x squared. And then we're going to go to the table and plug in 4. So when I delete all those old ones, plug in 4, and what do you get? 16. Perfect. So at this point, I need to go check the point 4, 16, which I know it comes from stationary, to find out, is it a max, is it a min, or is it neither? Are you with me? But at this point, I have no idea. Why do I have no idea? Because I don't have the graph. So again, you could do the sign chart, plug into the derivative before, plug into the derivative afterwards, see what happens before 4, see what happens after 4. Or what I recommend is to graph it. But in order to graph it, you need a window. I need to know where to start, where to end, where to start, where to end. This is the tricky part, okay? But it's all based on what you need to see. So what do I need to see as far as the x's? 4. So let's talk about the x-axis. If I need to see 4, what should you start at? Should I start at 4? No, what should you start at? 2, 3, I'm going to start at 0. What should I end at? 6, 8, all those are fantastic. How did I get that window? Because I based it around what I needed to see. Are you with me? No one's going to give it to you. You have to figure that out. What do I need to see about the y's? 16. So maybe we're going to go from 0 to what? To 20, maybe 30. All those are good. Let's do 20. Could we change it if we want to change it later? Sure. So I'm going to count by 5s. And the answer is 4 and 16. So I know I need to see that point. Have I created a window around 4 and 16? So now let's go look at it. So I go to the calculator, window. We decided to go from 0 to 8, 0 to 8, counting by 2s. And then the y's, we decided to go from 0 to 20, counting by 5s. Now again, we can change this later. We did build a window around what we needed to see, and adding some algebra. Notice that it's negative x squared. What does x squared look like? Parabola, but it's negative x squared. Happy face or sad face. So if you know your functions, which you should, you would know ahead of time that you're going to get a sad face. Okay? Now, that's what it looks like. And we can always adjust it. If you don't like it, you want it taller, shorter, you could do all that. But now that I have the picture, what do I know I have now? A local max. So we've just verified that we have a local max at 4, 16. Now, could I have made a sign chart? Yeah, I would have made a sign chart at 4. I would have plugged into the derivative numbers before 4, and I would have gotten positives, which means it's going up. After 4, I would have gotten negatives, which means we have a max there. So a sign chart's not bad. It's just different. But I like having a graph. And here's another way I like having a graph. Some of you are like, wait a minute, didn't we do this stuff before? We kind of did. There's the maximum. How do I do maximum in the calculator? What do I press? Second, trace for calc. Number 4 for maximum. Go to the left of it, enter. Go to the right of it, enter. Guess where you think it is, enter. And you can verify that you're correct if you have the graph. But again, I'm making it sound easy. Some of you aren't going to be able to figure out the window, so you won't see the graph, so you won't be able to verify it. So there is some work involved. But have we been preparing since day one how to graph, how to do algebra, how to do work? It's all leading to this. Are we okay? Now, having said that, we just need to practice, practice, practice. We've done 2 examples. We're going to do 2 more. And I do want to talk a little bit about the singular. We will be getting into singular a little bit later. But I just kind of want to do a quick singular lesson just to give you a little introduction before we do our next example. And we'll add a domain in there. So let's talk about singular right here, okay? Singular. What does it mean to have a singular? Okay, now, first of all, pretend that these are derivatives. 1 over x, 1 over x minus 2, x plus 3 over x minus 1, and x minus 2, x plus 3 over x minus 5, x plus 4. Pretend somehow that all 3 of these are derivatives. Just somehow, mathematically, they all ended up being my derivatives. Not my originals, but my derivatives. If these were my derivatives, looking at the first example, what number could you plug in that would make this undefined? The answer is 0. Because if you plug in 0 into the derivative, we're pretending they're all derivatives, what's 1 divided by 0? Undefined. So the only time you're going to have singular, number 1, is when there's dividing. Number 2, there's got to be a variable in the denominator. So I want you to find the singular points for the next 3. Find the singular points for the next 3. In the first, example number 2, what would make it undefined? 2, because 2 minus 2 is 0, can't have 0 in the denominator. What would make the third one undefined? 1. Is that it? What about the top? What about -3? It's fine. Exactly. What about it? You can have 0 in the numerator. It's not the problem. The only problem is in the denominator. So it would be just 1. What would make it undefined in the last case? 5 and -4. Okay. What about the top? It doesn't matter. It's not about the top. It's about the bottom. But remember, if I gave you, let's add a 5th case, x squared minus 4x plus 3. Does this have any singular points? If this was the derivative? Is there any dividing? Is there anything in the denominator? No. So this would be none. What about this one? Again, something weird. X plus 3 over 5. If this was my derivative, what number would make it undefined? Oops. Oh, it's like a mystery there. Okay, so what would make that undefined? None. If you said -3, the numerator is not the problem. It's only the denominator. Are we okay? Now, I'm going to give you another one to try. It's a little bit more complicated, but let's say you find the extrema of f of x equals 1 over x. There's no domain. Find the stationary, singular endpoints, and if you're fast, make the table and keep going. If you're fast, make the table and keep going. But some of you are going to get stuck right off the bat. Set it equal to 0 and solve. Okay. But in order to take the derivative, number one, I'm going to have to rewrite this as x to the negative 1. So know how to do that. Then the derivative is going to be negative 1x to the negative 2 and set it equal to 0. So if you can't take the derivative, that's problem number 1. Then problem number 2, which is probably going to be the biggest problem of all, is algebra, algebra, algebra. So if you struggled with this would be negative 1 over x squared. Remember how I kept telling you I like to make the exponents positive? Here's why. This will be equal to 0. Now, how do you solve this? 2 ways. 1, a proportion, or 2, clearing the fractions. It's really the same thing, but if I call this 0 over 1 and you cross multiply, 0 times x squared is 0, the variable's gone. Negative 1 times 1 is negative 1. Does 0? No. So what's the answer? No solution. Do you remember that in algebra? Where sometimes there is no solution. But for us, what does that mean as far as stationary? None. But again, what caught us was the algebra. Sometimes there's no solution, sometimes there's all solutions. And there's a couple ways of doing that. Okay? Now, when I look at the derivative, which is negative 1 x to the negative 2, or how I like to write it, here's why, negative 1 over x squared, do we have any singular points? What is it? 0. If you plugged in 0, you would get undefined. And again, see that whole rewrite it? Like, I don't want to rewrite it. Here's how it helps to rewrite it. Then, were we given a domain or anything in the beginning? So is there any endpoints? None. So when I make my little table, the only number we're going to look for is what? I'm going to plug it into the original. Now, we can kind of do this in our heads. If you take 0 and plug it into the original, what's 1 divided by 0? So that is, no, 1 divided by 0 is undefined. So wait a minute. There is nothing at 0. So do I have a max? Do I have a min? What do I have there? I have neither. I have nothing going on there. I have nothing going on there. And then you're like, what? What do you mean nothing going on there? Let's graph this around 0 and see what it looks like. So if I want to see around 0, what would be a good window for x? What to what? Negative 5 to 5? Cool. What about the y? We don't have anything we're plugging in, so maybe the same. Negative 5 to 5. So let's do that. So again, we build a window around what we want to see. So we go to our calculator, go to y equals, get rid of the y1, put 1 divided by x, and let's go see why there's nothing at 0. Well, we go to window, we're going to do negative 5 to 5, counting by ones, negative 5 to 5, counting by ones, and again, we can make it larger, make it smaller. We're just kind of guessing at this point. Press graph. What do you notice? Is there a max or a min at 0? Is there a max or min at 0? No. What do we have at 0? What's this called? A vertical asymptote. So we don't have any maxes. We don't have any mins. There are none in this graph. This graph has no extrema. So that's even a possibility as well. Are we okay? So again, you're like, ooh, I thought this was going to be easy. Then I realized the algebra could be harder. The derivative could be harder. The graph could be harder. And the answer is yes. That's why we're going to have to do a bunch of examples. Okay? Speaking of examples, this was a little bit more on the weird side. Let's do one a little bit more conventional. So I'm going to give you a function. And for the first time, I'm going to give you a domain. So the domain for this one is from -1 to 5, which means the graph must begin at -1. and the graph ends to exist at 5. Okay, so that also helps me a little bit when I go to graph. That's going to help me a little bit but when I go to graph. Okay, so having said that, you have the function x cubed minus 6x squared plus 9x plus 1. I want you to find stationary, singular endpoints, and depending on you, do the whole thing, which means find stationary singular endpoints, make the table, make the graph, and label if you have any extrema and what it is. So I'll give you a good bit of time. Give that a try. All right, let's go ahead and go over this one and see how we did. So as we go over this one, number one, we take the derivative. This would be 3x squared minus 12x plus 9 and set it equal to 0. And then some of us got stumped. Why? You have to be able to solve this. This is algebra, algebra, algebra. So what could you have done? You could have factored out a 3, which leaves you with x squared minus 4x plus 3. Set that equal to 0. Then you could have factored this. This would be x minus 3, x minus 1. Then you would set each piece equal to 0. X minus 3 equals 0. X minus 1 equals 0. Add 3, x equals 3. Add 1, x equals 1. Okay, so we have 2 possible stationary points at 3 and 1. And some of you said, wait a minute, isn't this quadratic? Didn't he give us quadratic formula in the calculator? Couldn't I just done that? Absolutely. Now, I don't have it in mind offhand, but I just went to the internet real quick. And if you have a quadratic formula like you're in a calculator, A is 3, B is negative 12, and C is 9, it does it for you. So if you sat there and waited for me to factor it for you and didn't even think that you had a quadratic formula in your calculator or at that thing, that's we don't want to leave stuff blank. But again, you should know how to factor. You should know your algebra. Okay. Number 2, singular. If you look at the derivative, do we have any singular points, something that makes that undefined? None. Why? There's no dividing. There's no x in the denominator. There's no way this could ever be undefined. It's only when you're dividing and there's a variable in the denominator. So that's done. And then what about endpoints? For the first time, we're given a domain. So we have 2 endpoints, -1 and 5. So at this point, we have 4 possible extrema. I don't know if they are. I don't know until we actually do it. So we're going to make a table. And we're going to check 1. We're going to check 3. We're going to check -1. And we're going to check 5. These 2 come from stationary. So we know what they're going to look like. Top of a mountain, bottom of a valley. And these 2 come from endpoints. We know what they're going to look like. Where they begin, where it ends. And are we going to plug it into the original or the derivative? The original. It's all about the original. Okay, so we go to the calculator, we go to y equals, and in y1 we put the original, which is x raised to the 3 minus 6x squared plus 9x plus 1. We go to the table, second graph, and we plug in the points. The points we have are 1, 3, -1, and 5. Okay, so we have those. We have those. We go to the table. 1 gives you 5. So we're going to go look at the point 1, 5. 3 gives you 1. We're going to look at the point 3, 1. -1 gives you -15. -1, -15. And 5 gives you 21, 5, 21. Now, if this was a sign chart, you'd have to put all those numbers, find the betweens, it could be really complicated. Okay? But the other way, which is why I like, is the graph. You have to understand the graph. Now, what's the x-axis going to be? What to what? It has to be -1 to 5. Now, some of you are saying, shouldn't we go a little bit before and a little bit afterwards? And the answer is no. A domain means it begins to exist at -1 and it ends to exist at 5. So when you're given a domain, it's actually like a help. You know where to start, you know where to end. But we also have to figure out the y. So the lowest one is -15. How low do you think we should go? Maybe go down to 20. And the highest one is 21. Maybe go up to what? 25. And what do you want to count by? 5 5s, yeah. Be a little lazy. But again, nobody is going to give you the window. You have to figure out the window yourself. And I'm going to pause here, give you a minute if you didn't get that far, get the window, and then label, do you have a max, a min, or neither? A max, a min, or neither? A max, a min, or neither? So -1 to 5, counting by 1s, -20 to 25, counting by 5s. So we're going to go to window, 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 -1 to 5. And again, I'm being a little strict on that because it's a domain. Begins to exist at -1 and it ends to exist at 5, counting by 1s. And then the y, we have to kind of work around it. So -20 to 25, counting by 5s. Press graph. Okay, that's what it should look like. And you're going to notice sometimes you want to plot the points first to make sure everything fits. So for example, 1 5 is right there. 3 1 is right there. -1, -15 is there. And 521 is there. So you get that nice smooth curve. And then if we go one by one, what do we have at 1 5? Local max. What do we have at 3 1? Local min. What do we have at -1, -15? Is it a min or is it a max? Now again, some of us are a little confused there. Are you going to walk down to it or walk up to it? Walk down to it. That is a local min. Now again, another way to talk about that, this is a max because left and right are lower. This is a min because left and right are higher. We don't have a left, but the right is higher, therefore it's a min. Gotta walk down to it. And then what about this one? Local max. So in this case, we have 4 extremas. 2 are stationary, 2 are endpoints, and we have 1 5 is a local max, 3 1 is a local min, -1, -15 is a local min, and 521 is a local max. Okay, now I'm going to give you one to try at home, and I'm going to do one problem before we leave. That's a little weird. I want to get that weird one out of the way. Okay, so for next class, I want you to find the extrema of this one. Find the extrema of this one, of x cubed minus 9x squared plus 24 minus x. It's very similar to the one we just did. And I'm going to add a domain of, let's say 0 to 6. Let's add a domain of 0 to 6. Okay. And then make sure you practice. Give this one a try for next class. Make sure you practice. It's very similar to the one we just did. Okay. So please don't come blank. Practice this for next class. Now, the one I also want to cover before we leave is this one here. You're going to get some problems that are looking at it from a derivative perspective and looking at it from an original perspective and vice versa and back and forth. So this one says, the graph shows the rate of change, derivative of the price of eggs over a 70-month period where ET is the price of a dozen eggs and T is the time, determine when the eggs are rising and falling, blah, blah, blah. So basically, you have a graph, not of the original, but it's a graph of the derivative. So let's be clear about that. This is not a graph of the original. This is a graph of the derivative. And T stands for time from 0 to 70 months. From the graph of the derivative, we're going to do a graph of the original. Now, this is going to be weird. I'm going to go really slowly. I'm going to try my best to explain it, but you're going to have to kind of bear with me a little bit. Okay? So, are we agreed that this goes from 0 to 70 months? So we're comfortable with that? 0 to 70 months. Now, here's where it gets weird. From 0 to 10, from 0 to 10, from 0 to 10, notice the derivative is positive or negative. The derivative has a negative result. Negative result, when a derivative is negative, that means the graph is going downward. The graph is going downward. The graph is going downward. How do I know the graph is going downward? Because the result of the derivative is in the negative. Are we okay? Then at 10, it's 0. The derivative is 0. We'll talk about that in a minute. Then from 10 to 50, notice that the derivative result is going to be positive. So that means from 0 to 50, the graph is going what? Up. Now, I don't know how much up or what the angle is, but I do know that it's going up. And notice that it was negative, and then after 10, it became positive. So what do we have here? We have a local min. Then at 50 to 70, what's the derivative going to be? Which means that at this point, it goes downward. And at 50, we have a local max. Now, that is totally weird, and I get it. But that's how to go from a derivative to an original. But for next class, make sure that you try this one, stationary singular endpoint, do the table, do the graph, and label everything.